Swayam Prabha. Digital India. Educated India.
Hello and welcome to this another lecture on the course on control systems, and in the previous lecture we started discussing this, or started rather building up these tools or platform for discussing the Routh-Hurwitz criteria. We haven't even introduced what it is yet, but we are trying to sort of motivate discussions along that direction, and in the process we are trying to build up certain tools and certain observations which do not require very sophisticated mathematics, in the sense that you only require an understanding of complex numbers and their properties, like how their phase changes, yeah, and some properties of complex functions in complex variables. Okay, not very deep, I would say, in the sense that what would normally be expected maybe 50 years ago if someone were to study the proof of Routh-Hurwitz criteria. Okay, life is much simpler compared to that. Nonetheless, maybe it requires a little bit of an involved or focused attention on what we are doing here. So to reiterate, what we have just established is, okay, I haven't established both sides again, but you have to believe me on that. What we have actually established is that if you have a polynomial, all of whose roots are on the left half plane, the open left half plane, then if you pass arguments to that polynomial from the imaginary axis, right? So that means in place of s, if you substitute j omega and you keep changing omega from 0 to infinity, then as you keep increasing this omega from 0 to infinity, what happens to the polynomial is that its phase keeps increasing monotonically from 0 to n pi by 2, where n is the degree of the polynomial. What I argued was that this is not just a necessary condition for a polynomial to have all its roots on the left half plane, but this is also a sufficient condition. In other words, instead of going about it in the forward manner, if we go in the reverse manner, that is, if we first plot somehow this pj omega and look at its plot, right? So if you pass this argument for different omega along the imaginary axis, the positive imaginary axis, and if we plot this pj omega on the complex plane, where the real axis is basically the real part of pj omega and the imaginary part is the imaginary axis is the imaginary part of pj omega, right? If we plot it like that, then we will notice that if this plot goes across n quadrants, which is what essentially a phase change of n pi by 2 entails, if it goes about monotonically increasing its phase across n quadrants as omega goes from 0 to infinity, then we might also deduce, that is the reverse argument, that the original polynomial has all its roots on the open left half of the complex plane. Okay, so let's start by seeing a few consequences of that. The slide you see before yourself now is basically what we discussed in the last lecture. We ended the last lecture with this, and we showed you that this blue plot is coming from some polynomial which violates this condition, and therefore you might easily deduce that if this polynomial p hat, let's say, if it does not satisfy this condition, then p hat, what I mean by inadmissible is that this is inadmissible plot for a polynomial p which is supposed to have all its roots on the open left half plane. So of course it can be the plot of a polynomial, but then what you might deduce about that polynomial is that it does not have all its roots in open left half plane. So that is what this inadmissible means. Okay, it is inadmissible as a polynomial which can lead to the poles of a stable system. In that sense it is inadmissible. Okay, it cannot qualify as a polynomial whose roots are the poles of a stable system. Bibo stable system. That is what we mean by that inadmissible. So I thought that requires a bit of clarification. And that is not to say that this inadmissible means no polynomial can have a plot like this. Of course, polynomials can have plots that look like this, but in that case, they cannot come from systems whose poles are given by the roots of such a polynomial. Okay. So then, what is the next consequence that we see here? Suppose now we are dealing with only polynomials whose roots are on the open left half plane. So this is, let us say, the real part of p j omega, and this is the imaginary part of p j omega. So we have seen already that at omega is equal to 0, it starts from some positive real axis if a n is positive. So it goes like this. Let us say, I do not care about the magnitude really, I am drawing a qualitative plot, something like this, it goes on, for example. So what do you deduce from this? You see, as this is the plot as omega increases, right? As omega increases, so omega is implicit here. As omega increases, this is how this plot revolves. What is the next observation we can make? Now remember, we have split up this p j omega into p real j omega plus j p imaginary j omega, and since we have already pulled out this j, so we can actually call this just a function of this omega itself. So we will drop this, it is just a function of omega alone. Okay. Now notice that leads to two different polynomials. What can I say about the zeros of these polynomials? Suppose, so how many zeros will these polynomials have? Suppose degree of p is equal to n is equal to say even, which is to say it is an even degree polynomial. Then this real part of this polynomial will have a degree n, and this part will have a degree n minus 1. Yeah, I hope this you agree with, right? Because if it is an even degree polynomial, then the highest degree will be even, and that will contribute to the real part only. So the real polynomial has even degree and the odd polynomial has odd degree, which is 1 less than the highest degree. Same thing can hold if it is 2m plus 1. So if suppose n is 2k, let me use a different color here. Yeah, for the sequel we will only discuss about one of these cases, even or odd. Yeah, the other one just follows straight away, it is really a no-brainer that way. So if n is equal to 2k plus 1, then this will have degree n and this will have degree n minus 1. So this is basically an odd degree p and this is basically an even degree polynomial. Okay. Now notice what happens if this has to cross over through n quadrants. Yeah, how many zeros does it have to have on the, which is to say that how many crossings of the real axis must it have and how many crossings of the imaginary axis must it have. Okay. Now I can understand that the last time it goes like crosses over like this, it may not need to cross the imaginary axis. So how many times does this cross? Take this example for here, for instance. Yeah, this is pi by 2, this is another pi by 2, this is another pi by 2, this is another pi by 2, and this is another pi by 2. So this is like 5 times pi by 2. Yeah, and in going through this 5 times pi by 2, you notice that here I have p imaginary equal to 0. Then I have, as omega is increasing, p real equal to 0. Then I have p imaginary is equal to 0. Then I have p real is equal to 0. Then I again have p imaginary is equal to 0. So what is this property? This is a property that is known as something called interlacing. Okay. So if I have to have n such quadrants traversed, then I must have a certain number of times that I must cross the real axis and the imaginary axis. How many times exactly? You see that the sum total what is this? 1, 2, 3, 4, 5. So if it's a fifth degree polynomial, the sum total of the imaginary and the real axis crossings is equal to the degree. So the first observation, sum of the total number of imaginary and real p j omega axis. So this is not the real and imaginary of the complex plane, this is the real and imaginary of the p j omega plane. Imaginary axis crossings is equal to n is equal to degree. In addition, I know that one of these polynomials, the real and the imaginary part is of degree n, the other is of degree n minus 1. Notice that one of them has a degree n, the other is of degree n minus 1. If it's an even polynomial, then the real part has degree n, the odd part has degree n minus 1. If it's an odd polynomial, the even part has degree n minus 1 and the odd part has degree n. Yeah. So now, what does this tell me? That if the total number of imaginary and real axis crossings are n, so one of the axis real or imaginary p j omega is crossed n minus 1, or rather I should say, if it's n, then I should say it's basically not exactly half. So if it's, so for even degree polynomial, let me split it up into cases. Even degree, yeah. So for even degree polynomial is crossed n by 2 times, and so is the other, and so is the other. Yeah, is that correct? Let me check for the fourth degree polynomial. So this is 1 crossing, 2 crossings, 3 crossings, 4 crossings, yeah, and then it might go potentially to 360 degrees like this. Yeah. All right. Yeah. So we'll have this these sort of crossings of this. Yeah. So if it's real, if it's imaginary, we'll have all of these. No. Okay. But now notice, for an odd degree polynomial, one of the axis is crossed n minus 1 by 2 times, and the other is crossed n plus 1 by 2 times. So which is which? Now you are going to look at this and you should be able to now immediately deduce which is the higher degree polynomial for odd. It is the imaginary part, no? So it's basically the imaginary part. Yeah, this has so many roots. So if the imaginary part is 0, then that is basically a real axis crossing, no? So this is basically a real p j omega. This has n plus 1 by 2 crossings, and this, the imaginary part of p j omega, has n minus 1 by 2 crossings. Remember, why so? Because when the imaginary axis is being crossed, it's the real part that's 0, when the real part axis is being crossed, it's the imaginary parts that's 0. So how many roots can the imaginary part have? In case it's an odd polynomial, the imaginary part is obviously an nth degree polynomial, it's higher degree. This is an n minus 1 degree polynomial. But we are saying this, it's got exactly half. Why? Now notice, again I cast your attention back to this example we had chosen the other day. Now notice that if you pull out this omega here, these are both polynomials in omega squared only, and if I had indeed taken some higher degree, these would have been actually polynomials in omega squared. Okay. So therefore, if I am focusing my attention to only the positive half of the imaginary axis, there is going to be half the number of zeros. The other half of the zeros are symmetric about this. Okay, I hope you get the point. So the point I am making is, but if there is a root here of the real part, then there is also a root here of the real part, because these are all even degree polynomials excluding the one, where is that example? Let me see, yeah, maybe here, yeah, excluding this one omega that you can pull out. See, this is an even degree polynomial, and this by nature it is already even degree. So you see, for an odd polynomial, if you want to equate this imaginary part to 0, how many roots do you have? One is omega is equal to 0, the other is plus square root of 31, the other is minus square root of 31. What about this? It is just square root of 103 and minus square root of 103, right. So those are your roots. So if you are just interested in the roots along 0 to infinity, you see that the roots are, one is at 0, yeah, then one is at square root of 31, and then one is at square root of 103. This is square root of 31 and this is at 0. Okay. All right. I hope that part is clear at least. No. So you see, similarly, symmetrically, at square root of minus 31 also this will have a root, and at square root of minus 103 also this fellow will have a root. But I am not interested in this part, so I am only focusing my attention on this, right. So now, how many such roots am I encountering here, right. So similarly, you can see that there are 3 such roots that I am encountering here, no. It is a cubic, remember it is a cubic. So this part is generating 2 roots and this part is generating 3, right. So total 5 roots, but of course one of them is at 0. So if I exclude the root at 0, then it's exactly 2 roots on this side and 2 roots on the negative imaginary axis, if I take the union of the roots of these real part and the imaginary part, that is. Not to confuse so much, but let us get to the bottom of this. What we then see is the question on hand, that if this monotonic phase property is to hold good here, if this monotonic phase property is to hold good here, what do I need? What I need is that the roots, the imaginary and the real parts, as I go along this complex plane, as I go along the positive part of the imaginary axis along the complex plane like this, these roots, I will encounter the roots of the, this is what, this is the root of the imaginary part is 0 here. So this is basically where Pi is equal to 0, this is where Pr is equal to 0. So as I go like this, these roots will alternate. That is what this interlacing property tells me, that is interlacing. So the roots of the even part and the odd part, or the real part and the imaginary part, will alternate as I go along this. So because remember, I started with the condition that if all my roots are on the left half plane, then I must have certain condition. What is that condition? That the phase must be monotonically increasing. These arguments, both of them go both ways. The only part I have not proved is that if it is monotonically increasing, then it must be having all its poles on the, or all its roots on the left half plane. I have not proved that. But remember, trust me that these arguments go both ways. So first I have all roots on OLHP. So that it goes both ways, it implies and is implied by monotonic phase increase of P of j omega. So this is PS has all roots on OLHP. This means monotonic phase increase from 0 to n pi by 2 for omega going from 0 to infinity. Now this is also equivalent or the same as saying what I have now exactly deduced, which is, it goes both ways, no? You see, if it is monotonically increasing from 0 to n pi by 2, then I must encounter the zeros or the roots of the real and the imaginary part in an alternating fashion. Similarly, if I encounter these roots in the alternating fashion, then the phase of this polynomial, of that such a polynomial, must go from 0 to n pi by 2 monotonically. So these are these are basically both way arguments. No? So roots of P real and P imaginary interlace along the imaginary axis. So more formally put, suppose P real omega squared has roots omega r1, omega r2, omega r3, so on till omega rm, yeah, and P imaginary omega squared has roots omega I1 less than omega I2 less than so on and so forth till omega I, say m minus 1. Then this interlacing property says, interlacing property says that I have 0. Obviously, the first one of this omega squared, let me not write omega squared, let me write omega for now, yeah, because I still have that omega inside. No? So, of course, the first root is 0. So, the imaginary part is 0 means it is purely real. So, then I have this 0, omega r1, omega I1, omega r2, omega I2, so on till I have finally I will have omega I m minus 1, I hope I am not counting wrong, omega I m minus 1 and omega r m. Okay, it starts with 1, 1, 1, 2, yeah, so that is it, that is exactly what it is. So this is what the interlacing property says. So now notice, if I go back on my argument here, if I go back to this diagram here, if the roots are interlacing, if the roots of the real and the imaginary part interlace, I have my answer to the question. So I started out with this question of obtaining a condition to ascertain if a given polynomial has all its roots on the open left half plane. And now I have given an answer, at least some sort of an answer. I say that, okay, focus on just the positive imaginary axis, pass on arguments from the positive imaginary axis, omega 1, omega 2, omega 3, keep increasing from 0 to infinity, and look for the roots of the real and the imaginary part, which is the even and the odd part of the polynomial. So split up the polynomial into the even and the odd part like I have in this particular example, and then look for the roots of such. So for example, here you see the original polynomial is cubic, but this polynomial isn't cubic. No, each of these individual polynomials are relatively easy to find the roots of. So here you see immediately the interlacing property doesn't hold, as we shall see probably later when we take up this example using Routh. We will see that this one indeed turns out to be a polynomial whose roots are not all on the open left half plane, but we have already reduced this based on our observation here. So what Routh will do is it will formalize this process, it will give us some more machination, some more tools at our disposal. Already with the study that we have done, we can try it out on this particular example here and deduce that this polynomial definitely, even without evaluating its roots, we can say that this polynomial's all three roots do not definitely lie on the left half of the complex plane, okay, because the interlacing property doesn't hold. Look, 0 and root 31 are two consecutive roots of this imaginary part, yeah, with nothing in between 0 and root 31, which satisfies as a root of the real part. So the interlacing property is violated here. I hope you see that, right? So between any two roots of the real part, there must be a root of the imaginary part. Between any two roots of the imaginary part, there must be a root of the real part. Here we see that between these two roots of the imaginary part, which is 0 and square root 31, there is no root of the real part, which is this, right? So therefore the interlacing is violated. So we can immediately already deduce, yeah. So this gives us a tool, but we will not stop at this. Now look, the question still remains. At the end of the day, although I claim that yeah, we are not solving for the roots, but in order to deduce in this particular example that I have given you, so notice that in this particular example that I have given you here, what did I eventually end up doing? What I ended up doing was solving for polynomials, but that is exactly what we are trying to avoid. Ultimately, if for example instead of a cubic polynomial, if this were a 20th degree polynomial, then these real parts and imaginary parts roots wouldn't be so easy to evaluate after all, would they? Here of course, because it's cubic, I brought it down, so both of them become quadratic and I can read off the roots immediately. But what if it's 20th degree? Then just knowing this interlacing property, the question still remains. I don't want to evaluate roots and I still want to ascertain a method of finding out whether all my roots are on the left half plane. I am yet to answer that. So what could be a strategy? Here's an idea. Given a polynomial, suppose the original polynomial I started with has all its roots on the left half plane. Can I in some clever fashion reduce the degree of this polynomial? Say it's a 20th degree polynomial, I do some operation to it and I reduce it to a 19th degree polynomial in such a way that if the original 20th degree polynomial had all its roots on the left half plane, the 19th degree polynomial should also have all its roots on the left half plane. Okay. If I can get from 20th to 19th that way, there is hope I might get from the 19th to the 18th in that way, from the 18th to the 17th in that way, and so on, and keep reducing. So can I come up with a strategy that will allow me to preserve this interlacing property? So notice what I am saying. What I am not saying is that the roots of the 20th degree polynomial, if there are 20 roots, then the roots of the 19th degree polynomial must be a subset of those 20 roots. No, I am not saying that. I am not saying that there is any direct relation between the roots of the original 20th degree polynomial and the roots of the 19th degree polynomial that I have obtained by reduction. I am looking for an algorithm which will allow me to reduce from the 20th degree polynomial to the 19th degree polynomial in such a way that if the original polynomial had this interlacing property, the 19th degree polynomial should also retain that interlacing property. What will be the benefit of such an algorithm? I can gradually keep reducing the degree of the polynomial, 20th to 19, 19 to 18, 18 to 17, so on, until I come up to a manageable degree, maybe a second degree polynomial. If I want at that juncture, I can evaluate the roots, and so I can finally reduce, reversing the argument, yeah, that since this second degree polynomial has this interlacing property, the 20th degree polynomial I started with also has this interlacing property. So until as you noticed already here, the moment I came to this third degree polynomial, checking for the interlacing property became very easy. Yeah, I have already shown you that. Checking for the interlacing property of the third degree polynomial is very easy. Yeah, that kind of equations that I am dealing with at this level is very easy. But if I started with a 20th degree polynomial, this would have been a hopeless case. So the strategy would be, starting with this 20th degree polynomial, can I somehow, if the 20th degree has the interlacing property, the 19th will also have this interlacing property, the 18th will also have this interlacing property, and gradually can I come up with a third degree or a second degree polynomial where the interlacing property is easy to verify, and then I am done, because I will check for the interlacing of this 19th degree or of this third degree polynomial or the second degree polynomial, and I will reverse the argument. So because at every step I have kept preserving this interlacing property if it was true of the higher degree polynomial, that's why based on what I study of this third degree polynomial, I will say that if the third degree polynomial follows this interlacing property, the original 20th degree polynomial will also follow this interlacing property. That is the idea. So how can I do this? It turns out that this is where this Routh criteria, this special smart way of doing this helps us. Okay. So how so? So for example, what you do then is, let us say you start with this PS, which is A0 plus A1s plus A2s squared plus dot 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 plus an minus 1 s to the n minus 1 plus an s to the n. Now clearly if you split this up, say n is even. Again for odd it is just a simple matter, you can convince yourself that it is not very different. I will just take n to be even. So now I split this up into A0 plus A2s squared plus dot 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 till an s to the n plus A1s plus A3s cubed plus dot 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 till an minus 1 s to the n minus 1. So I have now split this up into even and odd part. Now I pass this through p j omega and I see that what this becomes is A0 plus A0 minus A2 omega squared plus A4 omega to the 4 plus so on, then minus 1 to the power, I think it will be n by 2 if I am not mistaken, omega to the n, a n. I hope I am not making a mistake, I suppose I am not, but yeah, that should be it, plus j omega, you pull it out, this is A1 minus A3 omega squared plus A5 omega to the power 4 minus so on till you come up with a to the n minus 1, again a minus 1 to the power probably n by 2, I am not very sure, just check this numbering, I am not going to go into the nitty-gritties. So you split this up in this fashion. Okay. Now what the central idea is going to be at this point is, if you want to go from PS to an n minus 1th degree polynomial, how to do it? How to do so? So here is an idea. Okay. So you define QS is equal to, notice that if it is an even degree polynomial, then the highest degree coefficient must appear in the even part of the polynomial. So I want to get rid of this. Okay. I want to get rid of this. On the other hand, if this was an odd degree polynomial, okay, if this was an odd degree polynomial, then I would have wanted to get rid of the highest power in this. Of course, this would then be n plus 1. So I would have tried to get rid of this term. How do we do this? So what we do is, we take this, okay, let me name this P even, P odd. So what we then do is, we do not have any problems with this odd part you see in this case, because the odd part is already having the highest degree of n minus 1. But it is this even part which has this nth degree which we want to reduce. So what we do is, we retain the odd part as it is. To the even part, what we do is, from the even part of P even, we subtract suitable coefficient times S times P odd, but that will itself not make this term vanish, no. I have to also multiply this by this ratio of an upon an minus 1. Yeah. Notice what this does. Go back here. Notice what this does. What I am saying is, I am retaining this, the odd part here as it is, and I am subtracting S times an upon an minus 1 times the odd part from the even part. So then what I am claiming is that Qs is an n minus 1 degree polynomial. Not just that, the beautiful thing now is that if the original polynomial p had the interlacing property, then this, so again I have dropped this argument in S here, maybe you can put it back in. So the argument is that the claim is, of course this part of the claim is very easy to see, that it is going to be an n minus 1th degree polynomial. If you subtract this, no, so you are taking the even part and subtracting s times an upon an minus 1 times the odd part. The only thing you need then is that an minus 1 should not be 0. This is an important requirement. So later on we shall see that sometimes this singularity arises for several reasons, for some glitch in the system, and then we have to sort of take some precautionary measures or some bypassing techniques. But for the general case, let us say this an minus 1 does not vanish and we do not encounter this sort of a singularity. So what we do is, if we keep doing this, now notice at the first step Qs, we have managed to reduce the degree of the original polynomial p from n to n minus 1 in Q. But additionally, the claim is, if Ps meets the interlacing property, so does Qs and vice versa. So this is not just any arbitrary way of reducing the degree of the polynomial. Okay. In other words, we are actually achieving our goal. Remember a few minutes back what I said? I said that we want to keep reducing the degree of the polynomial through our algorithm, and if the original polynomial had the interlacing property, which eventually means from that flowchart diagram we have given here, that if the original polynomial has this interlacing property, then it has always roots on the LHP, open LHP. So now we are claiming that we have found a way of doing this, of reducing this. So if this works both ways, then there is nothing stopping me from performing the same type of operation on Q and getting to some Q dashed, then from Q dash to some Q double dash, and at each step subsequently reduce the degree from n to n minus 1 to n minus 2 and so on and so forth, right. So I am claiming that this interlacing property will hold, and that is what probably requires a bit of a demonstration. So let me just show this to you. It may take a while, maybe a few minutes, but I think it is worth the while to see that. So now notice that Q odd is the same as P odd. So again I say that there is nothing special about choosing a original polynomial to be even, just the arguments will be reversed. If you started with an original odd polynomial, then what you would have done is you would have got a Q where you would have retained the even part and you would have subtracted from the odd part of P s times an upon an minus 1 times the even part of P, okay, just the interchange, the argument holds. There is nothing special about an even degree polynomial or an odd degree polynomial as such, okay. Yeah. So what we are now saying is, notice, so observe that Q odd is equal to P odd, right. So therefore, if at omega is equal to omega 1, P omega 1 odd is equal to 0, then this is the same as Q odd, because they are of course the same polynomial, no. So they will have exactly the same roots, yeah. So they have the same zeros or the same roots, alright. So this is true. Now what about Q even? Q even is equal to this. There we have done some machinations. We have said that P even minus S times an minus an by an minus 1 times an upon an minus 1 times P odd. Now suppose P even P even vanishes at some omega 2 and omega, okay, let me write down the interlacing property then of the original of the P, that will make it easier. So suppose we have 0, then omega odd, or rather omega even, let me call it, omega even 1, then omega odd 1, then omega even 2, then omega odd 2. So this is for P, okay, this is for Pj omega, right, then omega even 3, so on and so forth, okay. Now for Q we still have this, for the odd part you see we still have this 0, omega odd 1, omega odd 2, so on. What we are required now to do is to check out if indeed for Q also we can find some omega, not exactly the same omega even, but some omega even star maybe, which are roots of the even part of this Q. So notice what happens to this fellow, okay. So here is our observation. So Q even at say omega odd 1 is equal to what? Q even at omega odd 1, so this part goes to 0, so this is equal to P even at omega odd 1, and what about Q even at omega odd 2? This is also by the same argument P even omega odd 2. Why? Because this part vanishes, no, at omega odd 1, omega odd 2, P odd vanishes, that is the definition, that is the way we are defining this, no. So then notice that what is the sign of P even at omega odd 1 and what is the sign of P even at omega odd 2, yeah. Why am I asking this question? Because remember in the original case, now I can forget about Q, think of just this. So if you have a function, which has a root here, yeah, so this is maybe the omega even, and on two sides of it you have omega odd 2 and omega odd 1. So this is, let's say, omega even 1. So think of the plot of P even omega. What can you say? If there is a 0 here, then the sign of P even omega at omega odd 1 and the sign of P even omega at omega odd 2 must be opposite, because there is a 0 crossing here of multiplicity 1, isn't it? So either it is a plot like this or it is a plot like this. So what we can say is this is equal to this, yeah, correct, because now we are looking at the original polynomial. Because of the interlacing property of the original polynomial, you see the even one vanishes here, the odd one vanishes here, the even one vanishes here, the odd one vanishes here. So at these 2 points where the odd one only vanishes and the even one does not vanish, yeah, so we are assuming that there are no purely imaginary roots of the whole polynomial, so that yeah, so that the odd one and the even one cannot vanish at the same point. So that is why this strict inequality holds. So the odd part and even part cannot vanish at the same point on the imaginary axis. Okay. So think of this Pj omega. What happens to this even part and the odd part? The even part vanishes at a point like this. So the sign of the even part between two of its vanishing points, two of its roots, yeah. So if you draw the curve of this, so let us say this is the axis, so this is the omega even 1, omega even 2, yeah. So if there are two zeros, either the plot is like this, or the plot is like this, yeah. These are the two ways in which the P even part can evolve. It must be 0 at omega even 1 and omega even 2. So at omega odd 1, whatever its sign is, at omega odd 2 its sign must be opposite. Same thing here also, if here it is negative, then here it must be positive, and if here it is positive, then here it must be negative, no. So that tells us that the sign of P even at omega odd 1 must be the opposite of the sign of P even at omega odd 2, yeah. So now that we have seen this, based on this we can also deduce, therefore sign of Q even omega odd 1 is also the opposite of the sign of Q even at omega odd 2, is it not? Yeah. So what does that tell us? That tells us that between two roots of the odd part of Q, because remember the odd part of Q and the odd part of P are the same, so therefore whatever is a root for the odd part of P is a root for the odd part of Q, because of our clever way of choosing this reduction technique of the degree, no. So the odd part of the Q is the same as the odd part of P, retained. So whatever is a root for the odd part of P is a root for the odd part of Q. So now what we see is that between two odd parts, two roots of the odd parts of Q, the sign of the even part changes. So this then leads us to conclude there must be a root of odd multiplicity for Q even between two roots of Q odd. Why odd multiplicity? If it is even multiplicity, then you have the same sign. If you have repeated roots of multiplicity 2, then this thing does not hold true. Then you just touch this point and go back to the same side. The sign does not change. But the sign changes means that there might be either one root or three roots that are repeated at the same point, or 5 roots repeated at the same point. But now I am arguing that there cannot be more than one root. So this odd multiplicity is basically kind of like an artifice trying to mislead you in some sense. There cannot be more than one. Why? Because remember, between every two roots of the odd part there must be at least one root of the even part. And how many roots can the even part at max have? Exactly as many as the odd part, no. So therefore you cannot have more than one root of the even part between any two roots of the odd part, and you cannot have less than one root also, because the sign reverses. So therefore you have exactly one root of the even part between any two roots of the odd part, which is to say that we have found out a way, we have cooked up a way which says that PS respects interlacing is the same as QS respects or obeys interlacing. What that in turn means is that if PS had all its roots on the left half plane, then QS also has all its roots on the left half plane. Okay. So to quickly illustrate this with the example that we had chosen earlier, which was of course not corresponding to a polynomial with all its roots on the left half plane, probably we will consider such an example in the next class, but just to quickly test it out. So suppose you start with s cubed, as I did in the previous lecture, plus 10s squared plus 31s plus 1030. Okay. So now what I am doing is I am going to go, instead of cube, let me call it P1s. So P1s, look, I am going to retain the even part. because the even part isn't bothering me, it is not the highest degree, but the odd part I have to reduce. So how do I reduce the odd part? Here's how I'm going to do this. So s cube plus 31s, and I'm going to subtract some suitable multiple of the even part to get rid of this cube. So what do I have to do? I have to multiply by s by 10. No? So then I can get rid of the cube. So here's what I get then. So s cubed is gone, 31s minus, this is 1030 by 10, so that's 103s. So 31 minus 103, if I'm not mistaken, is 72. So we are left with 10s squared plus 1030 minus 72s. Alright. So you see minus 72. Yeah, I think I'm not making a mistake here. 103 minus 31 is 102, yeah, 72. That's right. Okay. Now I'll go to the next step. I'll act on P1 now. So now what is my problem? My problem is to reduce it from second degree to a first degree. So now I'll retain the odd part. But I'm going to get rid of this quadratic term. How I'm going to do that? Again 10s squared plus 1030 minus some suitable multiple of this 72s minus 72s. So what do I have to do this? I have to get it by 7.2. Okay, by 7.2. So then I notice that if I multiply it by 7.2, yeah, minus 7.2 rather, yeah, then I can actually get rid of this. Okay. So now I'm going to just consider this minus 72s plus 1030 alone. Yeah, because now I don't have any constant term here. 1030. Yeah, and you immediately notice, right, that using this reduction, in fact you could have noticed it at this stage also, you already notice that this polynomial P2 has a root on the right half plane. So it does not obviously satisfy the interlacing property. It does not satisfy the monotonic phase increase property either. So therefore you can say the same, that since this interlacing property isn't valid for this, the interlacing property isn't valid for this either. Yeah, because remember it goes both ways. If interlacing is valid for this, then interlacing is valid for this. If interlacing is not valid for this, then interlacing isn't valid for this either. You cannot have that interlacing was valid for this, but interlacing isn't valid for this. It goes both ways, no? So therefore at this juncture you can already conclude that this polynomial, even though I have not evaluated the roots of this, of course I had done this earlier also, I had shown you that the interlacing wasn't valid very explicitly by evaluating roots. But now I am saying that without evaluating roots, by a polynomial reduction technique which I set out to do earlier, I have done this. Okay. It turns out that this long division technique or whatever it is I am doing here can be captured very efficiently by something called a Routh array, and that is where the Routh array helps us. Okay. So let me just quickly introduce the Routh array by means of this very toy example that we picked here. What you do is, given this polynomial, say again s cubed plus 10s squared plus 31s plus 1030. What you do is, in the first line you write s cubed, s squared. So this is how you write the table, okay? And you will eventually see that what we are doing is actually that same operation that we have done earlier. So here you, in the first row you fill up from this, that's the odd parts only. So the odd polynomial 131. Second row you fill up with the even parts, which is 10 and 1030. Now from the third row onwards, what you do is you multiply this. So this is the shape that you have to remember. A very shortcut sort of a technique. This is the shape that you have to remember. Don't worry, we'll do plenty of Routh tabulation later on to show you how this is done. So for now, this is the operation. What is it? So this is 10 into 31, that is this, and then the minus sign here, so minus sign here. So this is a product and this is a product. So 10 into 31 minus 1 into 1030 divided by 10. So you have to divide by 10. Okay. In fact, we'll later see that for a Routh array, if you scale up a particular row by a constant factor, it really doesn't matter. Okay. You can take that as an exercise to check why it doesn't matter based on the arguments we presented. Okay. So what does it give us? It gives us 31 minus 103, that's minus 72. Okay. Then you fill up the last row. How so? Again you do this same operation. Of course you don't have anything here, so you fill it up with a 0 here. So this is minus 72 times 1030 divided by minus 72, which will give you 1030. Now notice carefully, the first two rows, they can give you P1, PS, if you know how to read them. How do we read them? S cubed plus 10s squared plus 31s, so you proceed like this, plus 31s plus 1030. The next two rows, they give you P1s. How so? So you read 10s squared minus 72s plus 1030. Notice what we had got here at the second iteration, 10s squared minus 72s plus 1030. At the last step, what you get is minus 72s plus 1030, which is nothing but what we had obtained here. So in a sense what I am saying is, instead of carrying out this rather cumbersome looking and this adjustment and all this, this tabulation does exactly the same thing. All that you have to remember is to go in this fashion. Okay, if you don't even remember that, now don't worry, we'll do plenty of examples, hopefully sufficient number of examples so that you are familiar with how this operation is carried out. It's just a shortcut. Okay, just like you have synthetic division for polynomials, which is a shortcut to the long division of polynomials that you might have learnt in high school, right? So similarly, the same operation that we are capturing, this step of our algorithm going from P to P1, P1 to P2, the same thing is being captured here. As I said, these two will give you P2 if you know how to read. So this is s cubed plus 10s squared plus 31s plus 1030, which is your original polynomial. At the first iteration, after cancelling out, after getting rid of the highest degree, you got 10s squared minus 72s plus 1030. Okay, and then acting on P1s to get rid of the quadratic s squared term, that is the highest degree term here, what you then got was minus 72s plus 1030. Okay, sounds legit. So far so good. So two observations I would like to make from this table that might help you. What is it that we are going to deduce then? The big reveal in all of this is, look at the first column of this table. Which table? This table. Okay. So what exactly am I looking for in the first column? I am looking for the, look at the signs of the numbers. So you see, you start with the first one, it's positive. Start with this one, it's positive. Then you go here and there's a sign swap, it's negative. And then you go again and it goes again from negative to positive. Okay. So it tells us that there are sign changes. So the first point that I am going to make, first point, if there are any sign changes as we go down the Routh array's first column, then interlacing does not hold. Why does interlacing not hold? Here is one important point here that we haven't mentioned yet and we have bypassed so far. Okay. What does it mean to have interlacing? Interlacing means all roots are on the left half plane. What does it mean to have all roots on the open left half plane? The coefficients of all the coefficients of your polynomial. So let's ask this question, why? So the answer is given by a necessary condition for all roots on OLHP is to have all coefficients of the polynomial with same sign. So either they are all positive or they are all negative. Why so? You just look at the factorization, no? You just look at the factorization, you have this an and then you have s minus pi to the ti. Okay, look at this. So if all of them are on the left half plane, then these are all minus pi is a positive number. So you are going to multiply everything with a positive number. So every sign is being determined by the sign of this an only. So if an is positive, then every coefficient is positive. If an is negative, then every coefficient is negative. Alright. So therefore it is a necessary condition. Clearly it is not a sufficient condition, because we have already seen that we started with a polynomial like this which had all its coefficients positive. I wish it were that easy, then we wouldn't need this Routh array, but clearly just having all the coefficients positive does not tell you alone that the polynomial must have all its roots on the left half plane. It is only true for quadratic polynomials. Okay, beyond quadratic it does not hold true, as is revealed here. But now, by the way, observe that even if pi is not real but a complex number with negative real part, even then you see when you look at this factor here, you see all the coefficients will still be positive, right. So you can, I leave that to you to check as an exercise, that even if pi were a complex number, because now if you have to have a real polynomial with real coefficients and its roots are complex, then they must appear in conjugate pairs. That is the key. So even if pi were not real but a complex number on the left half plane, even then this condition holds that all the coefficients must have the same sign. It is a necessary condition for all roots to be on the left half plane. As I said, clearly not sufficient. And this now also reveals to you why in the previous lecture when we talked about this an being positive and said that it starts from the positive real axis when this plot evolves, right, this Mikhailov plot or what it is called, it evolves, right, at omega is equal to 0, it starts from the positive real axis if an is positive, because if an is positive then by default a0 is positive, and a0 is after all the value of this polynomial at omega is equal to 0, right. So that is one crucial aspect that I really thought merited some discussion or some clarification. Okay, go back to this. So why is this big reveal happening from the Routh array? Notice what are these elements in the first row, in the first column, sorry. At some point in time these elements will appear as coefficients of either p1 or p2 or p. So at some stage or the other some reduced degree polynomial p1, p2, p3 depending on what the highest degree, we will keep on going in this table, no. So at some reduced stage of this polynomial you will encounter a polynomial whose coefficients have dissimilar signs, and therefore that reduced polynomial at that stage definitely does not have all its roots on the left half plane, and therefore no interlacing, and therefore because interlacing works both ways, the original polynomial also does not have all its roots on the left half plane. Okay. Another quick reveal, you do not even need to look at just the first row. At any juncture if you have any entry of the Routh table negative, or if there is a sign change, right, then you can immediately conclude that this polynomial cannot have all its roots on the left half plane. Why so? Because you see eventually that term at some point in time or the other will turn up in some form or the other in this, it will have a bearing. Okay. You can take that up as an exercise to check that not just the first column but any term of this Routh array, if the polynomial has to overall have all its roots on the left half plane, then no term on this Routh array can actually be of dissimilar sign to the others. Why? Again the same argument, no. See all of these terms, if you are cooking up PS, you are involving all of these terms. If you are cooking up P1S, you are involving all of these terms. So every term enters one or the other polynomial. So if any one of these fellows is defective in the sense that it has a different sign compared to other coefficients, then that particular polynomial which involves that term will have some root on the right half plane or maybe not on the left half plane, open left half plane. And because that polynomial at that stage does not have all its roots on the left half plane, every polynomial at preceding or succeeding stage also suffers from the same defect. Okay. It turns out that Routh array actually tells you much more. We have only painted half the picture. We have just answered the question as to whether a given polynomial has all its roots on the left half plane or not. And this Routh array, which is basically nothing but a more compact representation of this sequence of operations that we have carried out here, gives us that answer. But it turns out Routh array actually tells us much more. It also tells us exactly how many roots are on the left half plane and how many roots are on the right half plane, and that is to be counted by exactly the number of sign swaps in the first column. But our discussion so far do not make it very obvious as to why it should be so. So that paper which I told you, which appeared in IEEE Transactions on Automatic Control, yeah, that paper uses some sophisticated techniques to actually prove this. Not very difficult, based on whatever understanding you have now got of this Routh array. I hope that you will appreciate that that paper actually makes it much more accessible to undergraduate students. So if you are interested, please read that paper with this understanding of interlacing property and monotonicity and everything, and I am sure that you will find that paper much more illuminating. Okay. So what I am now going to claim, but maybe not prove so much, is the fact that not only is the sign changes in the first column going to tell you that the polynomial does not have all its roots on the left half plane, but if you count the number of sign swaps, so for instance here, what is the number of sign swaps? From positive you have one sign swap to negative, and then from negative you have another sign swap to positive. So there are basically two sign swaps. Again, don't worry, we will take more examples and we will show this in more detail. So there are two sign swaps. So this tells you that the number of sign swaps is equal to the number of roots on the right half plane. So therefore this polynomial has two roots on right half plane and one root on left half plane. Maybe we will give you some ideas about why this is true based on what is discussed in that paper, but that is all for next time, for the next lecture. So hopefully you now have a basic idea of how to construct a Routh array given any polynomial. Maybe we will take up a few more examples in the next lecture to make this clearer, but at least I hope that you are in a position to appreciate why this argument and this logic or this algorithm of reducing the degree of the polynomial successively to conclude about the roots or the number of roots on the left half plane actually works. Thank you.